This seismometer works because a suspended mass tends to remain in place through inertia. The clever bit here is that the instrument records the relative movement between this stable mass and its ground-mounted structure. Imagine a heavy pendulum hanging freely. When the ground beneath it shakes, the pendulum itself resists moving, at least for a moment. This resistance to change in motion is inertia, and it's fundamental to how we detect earthquakes. To understand this, think about what happens when a car suddenly brakes. Your body continues to move forward, even as the car slows down. That's inertia in action. Similarly, the seismometer's mass, often a heavy weight, is designed to be as isolated as possible from the ground's vibrations. It wants to stay still, even when the world around it is violently shaking. The rest of the seismometer, the supporting structure, is firmly anchored to the ground. When an earthquake strikes, this structure moves directly with the earth. The crucial measurement isn't the absolute motion of the mass, but the difference in motion between the moving ground-anchored structure and the relatively stationary suspended mass. This differential motion is what gets recorded. Early seismometers used a simple mechanical system to capture this relative movement. A stylus attached to the ground-mounted frame would trace a line on a rotating drum, which was connected to the inertial mass. As the ground shook, the stylus would move relative to the mass, drawing squiggly lines on the paper. This was revolutionary for its time, but it had a minor setback. The minor setback was that these mechanical systems, while ingenious, introduced their own limitations. Friction from the stylus on the paper could dampen the true motion, reducing sensitivity. The resolution of the paper record was finite, making precise analysis challenging. Furthermore, the physical act of recording could interfere with the very freeness the inertial mass needed to maintain its stillness. The resolution to this challenge came with the advent of sensory electronics. Modern seismometers replace the mechanical stylus and paper with sophisticated sensors. These sensors detect the minute changes in position between the inertial mass and the ground-anchored frame without physical contact or significant friction. This allows for much higher sensitivity and accuracy in recording the differential motion. Instead of drawing, these electronic systems convert the relative displacement into an electrical signal. For example, a coil attached to the mass might move within a magnetic field fixed to the frame, generating a voltage proportional to the motion, or optical sensors might track the mass's position. This digital data can then be transmitted, stored, and analyzed with incredible precision, far beyond what paper records could achieve.
While electronic recording vastly improved data quality, a single seismometer, even a highly sensitive one, still faced a fundamental limitation. It could only effectively measure motion along one specific direction. Earthquakes, however, don't just shake the ground up and down or side to side in a single plane. They are complex, three-dimensional events, moving the Earth in all directions simultaneously. The bigger problem is capturing the full, intricate dance of an earthquake. Imagine trying to describe a complex ballet performance by only watching the dancers from a single fixed viewpoint. You'd miss so much of the depth, the turns, and the leaps. Similarly, a single seismometer, oriented vertically, would only tell us about the up and down motion, ignoring crucial horizontal shifts. For a long time, fully understanding the three-dimensional nature of seismic waves was a challenge. How could you design an instrument that simultaneously maintained an inertial reference point in multiple orthogonal directions, without the different measurement systems interfering with each other? It seemed impressive to even conceive of capturing such complex multi-directional forces with precision. The detailed methodology to solve this bigger problem involves using multiple instruments. Specifically, a modern seismograph station typically employs at least 3 separate seismometers, each carefully oriented to measure motion along a different axis. This array of instruments works in concert to provide a complete picture of the ground's movement during an earthquake. One seismometer is oriented vertically, designed to measure the up and down, or z-axis, motion of the ground. Its inertial mass is typically suspended by a spring, allowing it to move freely in the vertical plane while resisting horizontal shifts. When the ground moves up or down, the spring compresses or extends relative to the inertial mass, and this differential motion is recorded. Another seismometer is oriented horizontally, typically aligned along a north-south axis. Its inertial mass is designed to swing or slide horizontally, resisting motion along that specific direction. When the ground shifts north or south, the instrument's frame moves with it, while the mass attempts to stay put.
The relative horizontal displacement is then precisely measured. The third seismometer completes the spatial coverage, oriented horizontally along an east-west axis, perpendicular to the north-south instrument. This ensures that any horizontal ground motion, regardless of its direction, can be accurately decomposed into its east-west and north-south components. Together, these two horizontal instruments capture the full lateral movement of the Earth.
By arranging these three instruments orthogonally, one vertical and two horizontal at 90 degrees to each other, seismologists can capture the full three-dimensional vector of ground motion. Each instrument provides data on differential motion along its specific axis, and when combined, these datasets reconstruct the complete path and intensity of the seismic waves as they pass through the station. The electronic signals from each of these three seismometers are then digitized and combined. Sophisticated algorithms process this multi-axis data, allowing scientists to pinpoint the earthquake's epicenter, depth, and magnitude with remarkable accuracy. This comprehensive data is vital for understanding seismic hazards and improving building codes in earthquake-prone regions around the world. Furthermore, these individual three-component seismograph stations are deployed in vast networks across continents and even under oceans. By comparing the arrival times and characteristics of seismic waves at multiple stations, scientists can triangulate the source of an earthquake and map the Earth's interior, revealing its hidden structures and dynamics. It's a global listening system. So whether it's a single instrument or a global network, the fundamental principle remains the same. The useful part of a seismometer, its inertial mass, tries its very best not to move during an earthquake, allowing us to precisely measure the ground's violent dance around it.